This is for Year 11 specialists. We're going to look at more proofs. So we're going to look at question number 8. We're trying to prove that the diagonals of a square are of equal length and bisect each other. So there's actually two parts to this proof. We're going to prove that they're equal length and the diagonals bisect each other. Now, in order to start this proof, we need to draw a square. So I've arbitrarily labeled a square, and we've got diagonals, which we need to prove. I'll call the midpoints of that x. We need to prove that the lengths are equal to each other. So to start off, I need to define what OA is and AB are. So I'm just call that vector A and vector B. So the two diagonals in question are OB. So OB would be given by A plus B, and the other diagonal would be AC. So AC is given by negative A plus B. Negative A plus B. Now, we got to prove that the magnitude of that is equal to the magnitude of that. Since these are in A's and B's, and we can't really do much with them, we can't prove that straight away. So what you need to do is actually square it. So we needed to prove that the magnitude of that squared, which equals the magnitude of A plus B all squared, and the magnitude of AC all squared equals the magnitude of negative A plus B. This holds true because if the magnitudes are the same, then the squares of the magnitudes will also be the same. The reason why we use the squares of magnitudes is because we can use vector properties. So one of the vector properties I'm using is that if I have the magnitude of u minus v squared, say, that can be written as u minus v dot u minus v. So I can apply the same principle here. When I rewrite that as a plus b dotted with a plus b, similarly minus a plus b dotted with minus a plus b, I can check whether they're actually equal. Now let's do the dot product expansion. So this will be, knowing our dot product rules, that will be a dot a plus a dot b plus b dot a plus b dot b. That simplifies to a dot a, which is magnitude of a squared. I should put my lines, squiggly lines, plus 2a dot b plus b, the magnitude of b squared. Similarly, on this side, we've got a dot a minus a dot a minus b dot a minus a dot b plus b dot b. Again, we know a dot a is just a squared minus 2a dot b plus b dot b. Now, you notice how, and that's b dot b, magnitude of b squared. You notice how we've got some elements that are the same, but there's an element that's not. So that element and that element are the same. That element and that element are the same. These elements are different. So how can we prove that these are actually, the same magnitude, or the same square magnitude? The reason why that they're equal is, what is a dot b? A dot b is actually equal to, a dot b is equal to the magnitude of a times the magnitude of b cos of theta. Now we know this is a square, so a dot b happens to be 0 because they're perpendicular to each other. So since these are perpendicular to each other, that goes to 0 and that goes to 0. Therefore, we've proven that the magnitude of OB is actually equal to the magnitude of AC. So this shows that the side lengths, the diagonals of a square are actually of equal length. Now, the second part is a bit more tricky. We need to prove that they bisect each other. So I'm going to draw the shape very roughly again. We need to prove that they bisect each other. So OABC, we'll call that X. So the way I'm going to show that they bisect each other is to find out what OB actually is first. So we know that was A, that was OB. OB is given by A plus B. And we know that OX is given by half of A plus B. Now, we need a relationship to show that X is in the middle, or it bisects it. So the distance from here to here is the same distance from there to there. So the way I show this is I need to find, well, I want to find what AX is first. AX is given by AX, so we're looking at this resultant, so AX, this resultant, it's given by negative A plus OX. So that's why we found OX. OX is given by a half A plus B. A plus B. So negative A plus a half A plus a half B. So what we have is a half of B minus A. I'm going to make sure I put my lines on my vectors. Okay, let's get an expression for XC. X to C, so we're looking at that, so we're looking at this vector, XC, so this is the resultant. So to get to XC, you need the negative version of OX. So negative OX plus, that's OC is just B, plus B. So negative OX is the negative version of OX, which is just negative half of A plus B, and you add it to B. So what do we get? We get negative half A, negative half B, plus B. And what we get is, again, we've got half of B minus A. So we've proven that AX and XC have same direction and are of equal lengths. So therefore, the conclusion we can make is that our point X, X is the midpoint of vector midpoint. It doesn't need to be a vector, it's the midpoint of AC. So therefore it bisects it. Bisects AC. and we only need to do it for one because we know that the shape is actually symmetrical. So that's how you prove this is how you prove that the two diagonals of a square bisect each other, and they bisect each other at the midpoint x. Hopefully this helps.